So Ara is a quantum algorithms researcher at Agnostic. He holds an undergraduate degree in mathematics and physics and a PhD in engineering physics from McMaster University. Before working in quantum computation, he researched semiconductor hardware and atomistic simulation of nanoscale heat transport. Ara's casual interest includes music, film, and broad topics in science and computation. He's also an avid guitar and bass enthusiast. All right, so with that, I'm going to pass it on to her. Thank you.
Hi, everyone. I'm okay. I won't touch it anymore. Hi, everyone. So I'm Ara, and today I'll be talking about efficient quantum machine learning using hybrid computational resources. Okay, so quick outline. The first thing I'll address is what exactly is quantum machine learning. Spoiler, it's pretty much what it sounds like. After this, we'll talk about a kernel algorithm for quantum machine learning, and I'll also explain what a kernel is. Then we'll move on to how we actually implement quantum machine learning in practice, and I'll finish with a tutorial where we'll run a QML workflow using Covalent. So Covalent is a heterogeneous workflow orchestration tool developed by Agnostic, where I work. Okay, so quantum machine learning. We tend to think of machine learning as, on a very high level, as consisting of these three things, which are some sort of input data, a model, and a loss function. So the way that quantum computing overlaps with this is typically like so. So we can look at quantum information as being the input data, and we can look at quantum computations as machine learning models. So in this talk, I will focus on the latter, though the first is also a very interesting topic, maybe just a little bit outside the scope. Okay, so an intro to quantum computing. We've seen a few of these today, and a few wonderful ones, and you've seen that picture a couple times as well. This is the block sphere representation of a qubit. So what this illustrates is that unlike a classical bit that's either 0 or 1, for qubits we have a continuum of states on the surface of this block sphere. So what is quantum computing? It's sort of processing information using the laws of quantum mechanics. Or alternatively, it's processing information using a quantum system. The way that's described mathematically, for instance, here I have a quantum system that is a 3-qubit register. And we think of that, we represent that as a superposition of all these different 3-bit strings. So there are 8 of those, and each can be associated with a complex number, that is the amplitude, and so we have, in the end, a vector like this, okay? And so on a high level, the elements of quantum computation, we have operators that are unitary matrices. So what these do is to manipulate the different amplitudes. We have measurements that return outcomes with probabilities related to the modulus squared of those amplitudes. And we have algorithms that very broadly obtain desirable amplitudes and thereby reveal solutions. So how do we make use of quantum circuits for machine learning? The present-day perspective is to use a quantum circuit sort of as a subroutine inside of a classical machine learning algorithm. So you can imagine feeding a quantum circuit some sort of training data that gets embedded and then processed in some arbitrary way with a measurement that we use the results of to compute the loss and update our parameters and so on. So the particular machine learning algorithm that I'll discuss today is something called a support vector machine. So what is an SVM? Naively, the naive SVM is just a linear classifier. So here on my little graph here, I have 2 different classes of data. We have the blue class and the yellow class. And the objective of the SVM is to find a vector W and a scalar B such that W dot X minus B is 0. So that will be a line like this, where W is the normal to that line. And this is where it's 0. Here's what's called the margin, and that's the distance between these 2 classes. So what the SVM tries to do is find the line that maximizes this margin, okay? We also have over here, if you notice, a bunch of data points that sit right on the boundary, And those are what's called the support vectors. So this is where the name comes from. And the line that the top point sits on, for instance, is w.x minus b equals 1. The bottom line is minus b, w.x minus b equals minus 1. So up here, everything is a member of the class 1. Down here, everything is a member of the class minus 1. Blue and yellow. Okay, that's all well and good. But for this to be useful, we probably want to classify nonlinear things as well. So here, I mean, what line can I draw that actually separates these classes? Well, there really isn't one, right? So the solution here is to implement a feature map, which grabs our input vector, which has 2 components, and maps it to a new vector, where we keep the first 2 components, and for example, we just add a third component that's just the sum of the squares. So what that will do is it will turn this flat data into, it will add an extra dimension, basically. And with that extra dimension, we can just implement the SVM algorithm normally to find, in this case, the line is a plane, right? That separates the 2 classes. So what are kernels then? A kernel is essentially, in this context, an abstract measure of similarity. So a kernel can be associated with a feature map. So the way that's expressed mathematically is that the value of the kernel function, which is just the scalar, is the inner product of these transform vectors. So the reason this is useful for SVM is that the SVM only cares about inner products. So we can transform the data as we like within certain constraints, and then just feed that into our SVM to transform the data in a way that can be fitted. So what's a quantum kernel? Or how do we implement a quantum kernel? So we can think of starting with sort of a fiducial state of all zeros, and then we apply a bunch of operations that I've folded into a single unitary operator here. So what this will do is it will encode an input vector, and it will also do a bunch of parametric operations. And then we do that same thing, we apply the adjoint as well, but using the second input. So what we get is a kernel function like this. So kappa of x, x prime is given by the overlap of these two quantum states, right? So phi over here, 5x prime and 5x. And the feature map in this case is actually the density matrix representation of the vector. Okay, so the quantum SVM, what does that look like? This little diagram shows us what we're working with. So we'll start with embedding the training data on one side using the S circuit, and then we'll embed the second input using the adjoint of that circuit, and then do a measurement to check if we are in the 0, 0, 0 state. So why does that compute a kernel, or how is that useful? Well, if you think about applying these operators sequentially, if the 2 inputs are exactly the same, then the operators will be the same, and so the adjoint will pretty much just undo the first application. So this will undo this, and we'll end up with the 0, 0 state. So in this case, the kernel is 1, because we're going to get this every single time. However, in general, what you end up with is some other quantum state where the kernel function will not evaluate to 1. It will be a positive number, less than 1. Okay, QML in practice. So how do we implement quantum machine learning algorithms? The way we do this is to make use of all the great tools available in this ecosystem. So we have on one side classical algorithms, Python libraries like NumPy and sklearn. So you shouldn't really go implementing your own SVM when you can just grab one from here. And on the quantum side, we have programming frameworks like PennyLane and IBM Qiskit, and also HPC and quantum cloud services. So we can actually access QPUs over the cloud to do our computations. The role of Covalent in this context is it sits above our actual measurement script, and it seamlessly stitches these different aspects together. So onto the demonstration. So everything I'm about to show you is actually online in this repository, so if you are interested in trying it yourself, you can navigate to the Agnostic HQ GitHub page and take a look at this repo. I also have a challenge problem as an exercise for anyone who's interested, where we'll actually use IBM QPUs for real to do the computation I'm about to show you. Now I would like to switch screens somehow. There we are. Ooh, I don't like that resolution. Okay, that's better. Okay, so let's train an SVM classifier with a quantum kernel. Now, for the purpose of this talk, I'm going to use a simulator because there are only about a half dozen freely available QPUs, and we'd be waiting here for maybe 5 hours for this to finish because anything we submit will be queued up, right? So I'll just use a simulator for the purposes of the demonstration. What Covalent will do for us in this context is it will very simply parallelize all these tasks just on my laptop here. So let's walk through this right here. Just import some stuff. The data I'll use for the example is something called the wine recognition dataset. So what you're looking at is a bunch of wines from 3 different cultivators, which I've creatively named R, G, and B. And on the 2 axes, we have the hue and the intensity of the color of the wine. So the idea here is, can you tell which cultivator grew the wine based on these metrics of color? Okay? I've also cheated and just brought this up before we actually do it, just so you can see what the data looks like. Right, so let's define our quantum kernel function. So like I said, we're going to be checking if, after we apply the encoding and the adjoint, if we are back in the 0, state, which means we're checking the expectation value of this operator that's called a projector. You don't need to really worry about what that is, but here I just define it up here. I'll use random parameters for the circuit. And then to actually run this, I'll initialize a device instance using Penny Lane's lightning.qubit simulator. So here's my kernel function, and you can see it's very simple. I just grab this embedding provided by Penny Lane. QML is Penny Lane, by the way. It's customary to import it as QML. So yeah, here we just encode the first feature. We encode the second feature right after, and I'm going to grab the expectation value of that operator. So what we're doing here is actually just estimating the expectation value, right, over 1,000 samples. As a sanity check, let's make sure that our measure of similarity actually makes sense. So if I take two inputs that are the same, so if I look at x1 and x1, the kernel function should be 1, obviously, because they're the same thing. If I take 2 different inputs, I'm hoping to get a positive value that's less than 1. And finally, if you reverse the order of the arguments, they should also be the same value, right? The reason I've written approximately here is because we're actually estimating the expectation value, like I said. So we're running 1,000 shots of the circuit, and you can scale that up to 10,000 or 100,000, and this will get more and more accurate. So you can see that with 1,000 shots, this is sort of what we get. Where the kernel is 1, it's always 1, right? Because it ends up in that state for sure. Otherwise, here I'm comparing like x1, x2, and the kernel on x2, x1. So these numbers should be approximately the same. And indeed they are, right? But they're not exactly equal. And also we note that they're non-zero and they're less than 1. So great, we have a valid kernel function. So to use Covalent, what we want to do is take our computation and break it up into a bunch of granular tasks or granular processes. And what that is here for us is I have one function that grabs the data, and that's decorated with this electron thing, which basically tells Covalent that this is a little granular task. I'm breaking up the data into training and testing pieces, and then this function will actually call that quantum kernel over x1 and x2 in two different lists. So if you're not too familiar with Python, this is just a list comprehension. So what this does is basically loop over all I and all j, and it's just doing a matrix computation. So it's computing the kernel over all pairs in x1 and x2. Okay, and then I'm going to train the SVM classically. This is just the standard SVM implementation that I grabbed from sklearn, and finally just compute some metrics to see how it went. Okay. The last thing I need to do is write out my workflow using a covalent lattice. And you can see down here what I'm doing is just calling each of those electrons in the logical way. So I grab the data, I split it up, I compute my kernel matrices, and I train my SVM and grab the metrics. All right. So to actually run this, we need to dispatch it through Covalent. And to do that, we need to make sure Covalent is running. It is indeed. Okay, so let's submit. All right, so I've dispatched the task. If I click on this here to bring up the UI, oh, it's so tiny. There we go. So you can see the task running here. And you can see the sort of, this is called the transport graph. It's just a directed acyclic graph that describes the process of our computation. We can see that one of the kernel matrices is finished. Oh, the other one just finished. And OK, we're all done. So I'll come back here. Let's just visualize the results. And how did we do? Well, not amazing. So what we're looking at here, the X's are incorrectly classified points. The triangles are correctly classified points, and all the little dots in the background are just the training data. So you can see that the red cultivator R is rather more difficult to identify than the other two, where we have fewer X's. And to analyze this more precisely, we can look at what's called a confusion matrix. So on the left here, I have the true label, and on the bottom, the predicted label. So this is very, very easy to read. So what we have here is we look at cultivator R, and we see that 5 times it was predicted correctly, 10 times it was predicted incorrectly as being a part of G. So it thinks some of these points belong to the screen class over here. And it's never mistaken for cultivator B, which is not hard to believe. And then the other one, G, is more often classified correctly, and finally B is classified correctly every single time in this example. Okay. So I mentioned that we have a challenge problem as well. And let me just give you a quick preview of that if you're interested in trying it out. The solution's also up, so if you don't feel like figuring it out, you can just look at the solution. And what this will walk you through is getting an IBM ID and grabbing an API token that'll let you submit jobs to IBM QPUs. So to actually have any chance of running this, we're going to need to reduce the problem in size quite a bit, because we're using 5 to 7 qubit QPUs. These are the freely available ones. And you can see them here. Anyways. So yeah, go check out, please check out the challenge if you're interested in doing this. It's actually really cool. You get to use a real quantum computer. And if you change your mind, you can always cancel those jobs as well, okay? Right, so let me just get back to my slides real quick. The last thing I want to say is just a couple of resources, because I assume everyone here is fairly interested in learning about quantum computing. Qiskit, which is the IBM quantum programming framework, they have a great online textbook that walks you through pretty much everything you'd want to know about quantum computing at a really reasonable pace compared to, say, like a textbook on the subject. If you're interested in quantum machine learning more broadly, you can check out Penny Lane at pennylane.ai. And finally, please do visit the Covalent website at covalent.xyz and check out the Covalent docs, because there you'll find a bunch more tutorials and examples that you might be interested in. Okay, and with that, I thank you for your attention.
All right, thank you very much, Ara. If you can have a round of applause. Thank you. Agnostic is actually going to be, they actually have a table as well. Oh, we do have a question. Yeah, we can take one quick question. They have a table as well. If you guys have any questions, you can also go ahead and ask them tomorrow. They'll be there. We had Ian Buckley, who is the Quantum Community Manager and Partnership Manager at Agnostic. So if you guys have any questions, you can also go on and ask him tomorrow.
Join the Slack channel. The conversation is ongoing.
Okay, so are QPUs really that rare?
Rare
and expensive? Like you said, like there's half a dozen, like there's 6.
No. These are the ones you can get to for free. So you can just sign up for an IBM Q account, and just from the comfort of your own home, you can submit jobs to these particular QPUs. I'm not sure if Other organizations also provide a similar thing, but through IBM, you just get this handful here. There are plenty of QPUs out there, definitely more than half a dozen in total.
Okay, thank you once again, Ara. Thank you.
Thanks.